The gigantic explosion is a thought that has framed how we could decipher the universe, delineating the supporting progression of cosmology, according to Einstein's speculation. In any case, called core-swelling cosmology, the huge effect was the second the universe started its improvement, showing the development of all matter energy and presence. This occasion happened around 13.8, quite a while back, and prompted the beast universe we notice today. Anyway, late advancements in cosmology recommend that the legendary effect was probably not irrefutably the start. Rather, there might have been a stage before the monstrous impact that was similarly pivotal in molding the universe. This pre-period is known as boundless augmentation. This improvement is possibly one of the most entrancing parts of present-day cosmology. It recommends that before the hot, thick period of the colossal explosion, the universe went through a staggeringly fast, sensational extension. During this period, the universe extended at a surprising rate. To represent how outrageous this development was, assuming that the universe began more modest than a particle, it would have extended to be impossibly bigger than the whole detectable universe inside a minuscule part of a second, around 1/4 of a second. This extension stage didn't keep going long, yet it assumed a vital part in molding the universe. When the inflationary stage finished, the energy driving this development was delivered into space, warming it up and making the particles of issue that make up all that we find in the universe in numerous ways. Expansion was the forerunner to what we consider the tremendous explosion. While the hypothesis of expansion is broadly acknowledged in cosmology today, a few unanswered inquiries stay. For instance, we actually don't have the foggiest idea which began expansion, what compelled its stop, or how long it endured. These are open inquiries in cosmology, and responding to them is critical for a more profound comprehension of the universe's starting points. Before expansion, the universe was in a very thick little condition of issue, frequently alluded to as a peculiarity from the state expansion started, and at last prompted the development of Iota's particle stars and worlds. That the Titanic effect was the start of everything is charming, yet current cosmology recommends a more perplexing picture. A few hypotheses recommend that the universe went through a stage before the enormous effect. During this stage, expansion made the universe extend at a mind-blowing rate, expanding in size by a component of a trillion inside a negligible portion of a second. This quick extension was driven by a baffling type of energy that occupied void space. When expansion finished, the energy that had controlled this extension was changed over into particles, warming the universe and prompting the hot, thick state we call the huge explosion. This inflationary stage was cold and void. At this point, it set up for the arrangement of issue in the universe. As far as we might be concerned, one of the more hypothetical thoughts in present-day cosmology is the idea of everlasting expansion. This hypothesis proposes that expansion didn't shut down at the same time, yet rather stopped in discrete locales, making many pockets, every one of which could be a universe by its own doing. As per timeless expansion, there could be a boundless number of these universes, each with its own arrangement of actual regulations and constants. This is where the possibility of the multiverse becomes critical. The likelihood that our universe is only one of numerous or even a limitless number of universes. On the off chance that this thought is right, it could make sense of why our universe is so finely tuned for life in this multiverse situation. Each conceivable blend of actual regulations could exist in various universes, and we end up residing in one where conditions are ideal for stars to shape and for components like carbon and oxygen fundamental for life to exist, while speculations like timeless expansion and the multiverse stay speculative. The possibility of expansion itself is supported by observational proof. The most grounded help for expansion comes from the grandiose microwave foundation, CMB radiation. The most seasoned light known to man, the CMB, was transmitted around 380,000 years after the enormous detonation, when the universe had cooled enough for particles to shape. At that point, the universe became straightforward, and this light has been going through space from that point onward. By concentrating on the CMB, cosmologists can basically take a child image of the universe. This light gives urgent data about the universe's earliest minutes, assisting researchers with understanding what happened not long after the huge explosion and supporting the inflationary model. One of the main revelations came from the European Space Organization's Board satellite, which caught definite pictures of the CMB. These pictures uncover minuscule varieties in the temperature of the early universe, and these varieties match the expectations made by inflationary hypothesis. This observational proof builds up that expansion isn't a speculative speculation, yet a key piece of how we might interpret the universe. Starting points, understanding the enormous detonation, and what preceded it requires consolidating two of the main speculations in present-day physical science: Einstein's overall hypothesis of relativity. And quantum mechanics' general relativity depicts the huge scope construction of the universe, including the way of behaving of universes, stars, and planets. Quantum mechanics makes sense of the way of behaving of particles on the littlest scales to respond to the greatest inquiries in cosmology. For example, what lies under the surface for the universe, and where it came from. Researchers need to foster a hypothesis that joins these two frameworks. This would permit us to comprehend the enormous detonation as well as the circumstances that prompted it. One of the most captivating parts of the universe is its size. The most far-off objects we can see are around 47 billion light-years away. Importance: the recognizable universe is roughly 94 billion light. A very long time across. This might appear to be odd given that the universe is just 13.8 billion years of age. How could the discernible universe be bigger than the distance light might have gone in that time? The response lies in the way that the universe has been extending over the long run. As the universe extends, the distance between objects increments, making far-off objects farther away than the time it would take for light to contact us. Most researchers accept the universe stretches out a long ways past the noticeable universe. Truth be told, it's conceivable that the whole universe is limitless in size. The discernible universe is only the part we can see restricted when light has needed to go. Since the enormous detonation, there might be immense districts of the universe that we will always be unable to notice. Assuming the universe is endless, the inquiry remains: is there anything past the universe? Most researchers are questionable about this thought. Assuming that the universe is genuinely boundless, there is no external to it. The universe would essentially proceed with unendingly, regardless of whether the universe is limited. It probably won't. Check out to discuss something past. That the term past infers something beyond space, yet space itself is a property of the universe. Comparably similarly as the start of the universe is a subject of serious concentrate, so too is its definitive destiny. Similarly, as researchers